Arizona, 1970. Two prototype machines arrive at a copper mine for testing. Construction crews gather to watch the unloading. They've heard about what's coming, but nobody's quite prepared. 176 metric tons, 53 feet long, standing on tires 10 feet tall. The Clark 675, the world's largest wheel loader ever built.
Since every engineer and technician wanted to be the first to operate the world's largest tractor shovel.
The bucket alone holds 24 cubic yards. That's 40 tons of material in a single scoop. Dual Cummins engines, 1,400 horsepower, built to redefine what mining equipment could do. Clark's Equipment Company engineers are watching. They've spent 3 years developing this machine, hundreds of millions in tooling and testing. The mining industry is scaling up fast, and Clark believes this loader will dominate. The testing began. The machine moves, the bucket lifts, material dumps. It works, exactly as designed. Clark's executives are already planning production. They're convinced they've just changed mining forever. What they don't realize is that they've built a machine almost nobody will buy. Before we get into why this happened, quick thing. This channel explores industrial machines that changed construction, mining, and power dynamics. Not just the specs, but why some innovations dominate while others disappear despite being technically brilliant. If that interests you, subscribe. New videos every week analyzing the machines that shaped industry. All right, let's get back to Clark's expensive mistake. Here's the thing about the mining equipment business in the late 1960s. Scale was everything. Open pit copper mines were digging deeper. Coal operations were moving more overburden. Iron ore facilities were expanding faster than anyone had predicted. The equipment had to keep pace. Electric rope shovels were getting larger. Haul trucks were growing from 85-ton capacity to 150-ton, then 200-ton. And the support equipment, the loaders that fed material to the trucks, needed to match. Clark Equipment Company, headquartered in Buchanan, Michigan, saw the opportunity. They were already a respected name. They manufactured forklifts, a range of wheel loaders, construction equipment. In 1953, they'd even purchased Michigan Power Shovel Company and built a division dedicated to large-scale earth movement. But they lacked presence in ultra-heavy-duty mining. Companies like Marion and Bucyrus Erie dominated that space. Caterpillar was moving in. Komatsu and Laterna were developing bigger machines. Clark needed something dramatic, something that would announce their arrival in mining. In the mid-1960s, they'd introduced the Clark 475, a 75 metric ton loader with 700 horsepower and a 12 cubic yard bucket. Good machine, capable, but not extraordinary. So in 1967, Clark's engineering team started sketching something else. A loader more than double the size of the 475. Something that would make every competitor's machine look small. Development began with a problem nobody had solved before. See, you can't just scale up a wheel loader by 130% and expect it to work. Material stress increases exponentially with size. The drivetrain has to handle forces no existing components were designed for. The hydraulic systems operate under pressures that cause standard seals to fail. The tires have to support weight no production tire had ever carried. Clark's engineers weren't just building a bigger machine. They were inventing solutions to problems that didn't exist yet. Summer of 1970, they unveiled 2 pre-series units, powered by dual General Motors engines working in tandem because no single engine available could provide enough power. These prototypes served as testbeds. Arizona copper mines, brutal conditions. The engineers needed to verify everything: drivetrain stress, hydraulic reliability, structural integrity, operator ergonomics. The testing revealed dozens of issues. Components that worked fine on the 475 failed under the 675's loads. Systems that seemed adequate on paper couldn't handle real-world conditions. Clark went back to the drawing board. It wasn't until 1973, 6 years after development started, that the Clark 675 officially reached the market as a production model. The specifications were staggering: 53 feet long, about the same as a bowling lane, 176 metric tons gross weight. That's 390,000 pounds. Dual Cummins diesel engines producing 1,400 combined horsepower. Standard bucket capacity, 24 cubic yards, enough to hold 40 tons of material per scoop. But the most visually striking feature were the tires. 67-inch Goodyear tires, the largest production tires in the world at that time. Each tire stood over 10 feet tall. Each one was an engineering achievement in its own right, designed to distribute the loader's massive weight on unpaved, unstable mine surfaces. The two-engine powertrain provided not just power, but redundancy. If one engine failed, the machine could theoretically keep operating on a single engine at reduced capacity. And the price? Over $2 million in early 1970s dollars, which sounds like a bargain today, but in 1973, that was astronomical. The first few units went into service at major mining operations: copper mines, coal sites, large-scale earth-moving projects. And then the reports started coming back. Downtime, lots of it. The 675's size created maintenance nightmares. When a component failed, and components failed regularly, repairs took days, sometimes weeks. You couldn't just swap parts like you could on smaller loaders. Everything required special tooling, custom procedures, extended shutdowns. The tires alone were a logistics problem. If one failed, you needed specialized equipment just to change it. And replacement tires had to be ordered months in advance because nobody stocked them. The dual-engine system, meant to provide redundancy, actually created complexity. Synchronizing two engines wasn't as simple as Clark's engineers had hoped. When one engine developed problems, the entire machine often had to stop anyway because running on a single engine created unbalanced stresses. Word spread through the mining industry fast. Potential buyers started asking questions. How much downtime are the existing units experiencing? What are the real operating costs? How long do repairs take? The answers weren't encouraging. And then Clark faced another problem: competition. See, while Clark was developing the 675, other manufacturers were watching closely. Caterpillar, Letourneau, Komatsu, they all saw what Clark was attempting, and they all noticed the weaknesses. The 675 held the title of world's largest wheel loader for years, but it also served as a very expensive lesson for competitors about what not to do. Mining companies began making calculations. A single Clark 675 cost over $2 million and required dedicated support infrastructure. Or you could buy 2 or 3 proven loaders for the same money, spread your risk, maintain flexibility, and actually increase uptime, because if one machine went down, the others kept working. The math didn't favor the 675. By the mid-1970s, mining companies were telling Clark the same thing: we'll stick with smaller, proven machines. The 675 became known more as factory prowess than as a practical workhorse. Impressive to look at, difficult to justify. The numbers tell the story. Only 14 units were ever manufactured. 14 for a machine that took 6 years to develop and represented hundreds of millions in engineering investment. Of those 14, 2 were later converted to 675C specification, an upgraded version with improvements and refinements. But it was too little, too late. In 1976, just 3 years after the production model reached the market, Clark discontinued the 675. But here's where it gets interesting. The decision wasn't exactly official. Clark kept the 675 on their price lists and continued offering it for sale until 1988, 12 additional years. During those 12 years, not a single unit sold. Think about that. A machine sitting on the company's catalog for over a decade with 0 sales. Clark couldn't admit publicly that the 675 had failed, but the market had made its verdict clear. So what went wrong? The 675 wasn't a bad machine. The engineering was solid. When it worked, it moved material impressively. The concept made sense on paper. But working isn't the same as succeeding. First, timing. By the time the 675 was phased out, the mining sector was facing one of its worst crises. Commodity prices collapsed. Mining operations cut capital spending. Nobody was buying expensive, unproven equipment. Second, reliability. The few units in operation suffered enough downtime that word spread. Mining companies couldn't afford machines that spent weeks in maintenance. Third, and most critically, economics. The 675 concentrated too much value in a single asset. If it stopped, your entire loading operation stopped. No redundancy, no flexibility. Smaller loaders were cheaper to buy, cheaper to maintain, easier to repair, and provided operational flexibility. You could deploy them to different areas simultaneously. You could idle some during slow periods. You could get parts delivered within hours instead of waiting weeks. The 675 required everything to go right. And in mining, everything never goes right. While Clark struggled with the 675, competitors were learning from its failures. Caterpillar began developing what would become the 994 loader. Komatsu started drafting the WA1200. Letourneau worked on their L series. All of them designed machines close to the 675 specifications, but all of them paid attention to what killed the 675: reliability, parts availability, operational flexibility, support infrastructure. By the 1980s and 90s, these manufacturers had built successful large loaders. They'd learned the lessons Clark paid for. The irony is that today, modern mining operations use mining wheel loaders that dwarf even the 675. The technology advanced. Engines became more efficient, hydraulics more sophisticated, support infrastructure more robust. But those machines succeeded because their manufacturers understood what Clark didn't. Being the biggest isn't enough. Being the first isn't enough. You have to be reliable, maintainable, economically justifiable. The Clark 675 was none of those things. There's a broader lesson here about industrial equipment and market dynamics. Engineering ambition doesn't guarantee commercial success. Technical achievement doesn't automatically create demand. The mining industry wanted bigger loaders, yes, but they wanted bigger loaders that worked within existing operational frameworks, machines that could be maintained by existing crews, parts that could be sourced through existing supply chains, equipment that didn't create single points of failure. The 675 required mining companies to adapt their operations to the machine. That's backwards. Successful equipment adapts to operations, not the other way around. Clark also miscalculated the relationship between size and productivity. Yes, a 675 could move more material per cycle than two smaller loaders, but it couldn't match their combined uptime, flexibility, or redundancy. The real competition wasn't one 675 versus one smaller loader. It was one 675 versus multiple smaller loaders for the same cost. That's a fight the 675 could never win. Today, the Clark 675 wheel loader is largely forgotten. Most people in the heavy equipment industry have never heard of it. But it remains a unique piece of history, the world's largest wheel loader at the time of its creation, the machine that sat on the world's largest tires, a genuine engineering achievement, just not a commercial one. Standing as a reminder that in the world of massive machines, size isn't everything, until it becomes a liability. The Clark 675 wheel loader, a magnificent failure, and proof that being the biggest doesn't mean being the best. Sometimes the market rewards restraint over ambition. Sometimes smaller and proven beats larger and experimental. And sometimes the most expensive lesson in business is learning that just because you can build something doesn't mean anyone will buy it. If you found this useful, leave a comment. what other massive machines should have dominated but failed. I read every one. And if you want more stories about industrial equipment, construction economics, and machines that changed how work gets done, or didn't, check out these videos. Thanks for watching.